long solenoid. It has 450 circular coils, and those coils have a 2 centimeter diameter, and the current running through the solenoid is 1.75 amps. We're going to ask two questions. What is the magnetic field at the center of the solenoid? Then we're going to take our solenoid, stretch it out so it's not coiled anymore, it's just a long straight wire, then find the magnetic field 1 centimeter away. Okay, let's do A first. So for A, the length of our solenoid is 35 centimeters, 0.350 meters. The number of coils is 450. The diameter is 2 centimeters. The radius is 1 centimeter. And the current is 1.75 amps. We want to find the magnetic field at the center of the solenoid. We did this in our theory part in the last video. We found out that the expression for the magnetic field strength in the center of the solenoid is mu naught N times I over the length. So we have 4 pi times 10 to the minus 7 Teslas meters over amps times 450 coils times current 1.75 amps divided by the length of the whole thing, 0.350 meters, gives us a magnetic field of 2.83 times 10 to the minus 3 Teslas. Of course, magnetic field is a vector. Let's get the direction of that vector. So the current comes in around on the bottom. That's what this picture is showing. So our thumb goes this way on the bottom. We ask, what do our fingers do at the center? They point towards the right. So our thumb goes with the current, and then our fingers show the magnetic field. So the direction of the magnetic field is 2.83 times 10 to the minus 3 Teslas to the right, or I hat. So we'll take X, Y, Z the usual way. Part B, we take our solenoid and we uncoil it. Okay, so what exactly does that mean? Our solenoid starts like this, but we take it and we stretch it, and it ends up like this. So if we had a little paper clip turned into a coil, what we're trying to do is just stretch it out. Okay, so it started as the coil and it ends up as a long wire. Now what's the magnetic field? Okay, so we're going to try and find the magnetic field here. It's a distance of 1 centimeter from the wire, so R equals 0.01 meters. Here we have a long straight wire, so we'll use the expression for the magnetic field around a long straight wire, mu naught times I over 2 pi R. So 4 pi times 10 to the minus 7 Teslas meters over amps times 1.75 amps divided by 2 pi times the distance from the wire, 0.01 meters or 1 centimeter, gives us a magnetic field of 3.5 times 10 to the minus 5 Teslas. What's the direction of that magnetic field? If you have a long straight wire and the direction of the current, so we'll assume we kind of stretched it out the way it was, so the current went in on this side, so the direction of the current is this way. Put our thumb in the direction of current and we ask, what are our fingers doing here at this point? So my thumb is going with the current. My fingers at this point are pointing straight up towards the ceiling for me, into the camera for you guys. So coming straight out. So in the X, Y, Z coordinate system we have here, there's X, there's Y, there's Z. It goes in the Z direction, or K hat. These two magnetic fields are completely different by an order of magnitude of 100 and different in direction. And that kind of makes sense because a solenoid and a long straight wire are completely different things. They have different symmetries and they're just, they behave differently. So it makes sense that we don't get the same magnetic field.